Good morning, everyone. It is a pleasure to present our recent work titled Blockchain Enabled Self Autonomous Intelligent Transport System for Drone Task Workflow in Edge Cloud Network. This study is a collaboration between Chiang Mai University, Christiania University College, and Imperial College London. Our aim was to address critical challenges in autonomous drone systems, particularly cost efficiency, security, and scheduling through an integrated blockchain and deep learning framework. Let me explain for the background and motivation. In recent years, drones and autonomous vehicles have become central to intelligent transport systems, supporting applications such as package delivery, traffic monitoring, and emergency response. Despite these advances, current systems face major challenges: high processing and communication costs, weak data security, and inefficient scheduling in uncertain network environments. Traditional machine learning models are often centralized, which creates single points of failure and high resource demand, while blockchain-based approaches, though secure, introduce heavy computational overhead. To address these issues, our research introduces the Self-Autonomous Blockchain-Enabled Cost-Efficient System, or SBECES, designed specifically for drone workflow applications in edge and cloud networks. The goal is to minimize processing costs while ensuring security, privacy, and timely execution of tasks. For our system design and methodology, SBEX is built on a remote method invocation client-server model where drones execute lightweight tasks locally and offload complex processing to the cloud. The system integrates three main innovations. First, it uses deep reinforcement learning and Q-learning for adaptive scheduling, enabling drones to make intelligent task assignment under dynamic conditions. Second, it introduced a symbol blockchain with hybrid validation and fault tolerance, which ensures the integrity of workflow data and authenticates cloud functions at low cost compared to traditional consensus mechanisms. Third, the system explicitly models execution, communication, and security cost, and applies a serverless computing framework across providers such as Amazon, Google, and Azure to optimize performance. Drone workflows are modeled as directed acyclic graphs, where each task must be validated with blockchain hashing before execution, ensuring security and reliability. Yes, here are our results and contributions. We validated SBEX through simulations using iFog Sim and real drone delivery datasets. The results demonstrate a 30% reduction in processing costs and a 29% improvement in security and privacy compared to existing state-of-the-art solutions. The system also proved highly adaptable under variable network latency and workload sizes. It consistently maintained task deadlines and efficient energy consumption, extending drone mission lifetime. These outcomes show that SBEC not only enhances course efficiency but also delivers resilience and scalability for real-world intelligent transport systems. In summary, this research contributes a practical framework that integrates blockchain and deep learning to support secure, adaptive, and cost-efficient drone workflows, with strong potential for future applications in smart cities and multi-vehicle ecosystem. From research to classroom, teaching students about the integration of blockchain-enabled self-autonomous intelligent transport systems for drone workflows in edge cloud networks requires a carefully balanced approach that emphasizes both the technical knowledge domains and the pedagogical strategies that help students connect theory to practice in an engaging and critical way. Because this topic is inherently interdisciplinary, drawing from artificial intelligence, blockchain technology, distributed computing, reinforcement learning, and intelligent transport applications, and therefore demands that learners understand the foundational principles of each component as well as the ways these components interact in real-world scenario. The knowledge to be delivered begins with an introduction to autonomous systems and drones, where students learn that self-autonomous vehicles and drones function as intelligent agents capable of making decisions without human intervention, and that their usefulness spans applications such as package delivery, traffic management, surveillance, and emergency response, yet also carries challenges in processing, scheduling, energy consumption, and security. From here, instruction should highlight the role of distributed edge and cloud computing in providing the computational resources necessary for drones to process large-scale data, including sensor inputs like GPS, cameras, or radar, which generate massive amounts of information that must be offloaded to nearby servers to reduce latency, with students developing knowledge of the advantages and the disadvantages of edge versus cloud layers, and engaging in case studies comparing latency sensitive decision making at the edge with long-term predictive analytics at the cloud level. Building on this infrastructure layer, students should then gain knowledge of task scheduling problems in uncertain network environments, exploring why static scheduling approaches fail in dynamic contexts and why adaptive approaches based on reinforcement learning, such as deep Q learning and DRL-enabled schedulers, provide greater flexibility, with teaching strategies here including simulation exercise where learners experiment with scheduling algorithms under fluctuating bandwidth, workload, and drone mobility. So they directly observe how performance varies under different models. Alongside scheduling, the curriculum must cover the cost model introduced in the paper, explaining how execution costs, communication costs, and security costs are defined and calculated, and why minimizing these costs is critical to sustainable drone operations, especially in resource constrained or energy limited environments. And students can be asked to compute sample cost scenarios, comparing the outcomes when using traditional virtual machine services, container-based microservices, and the proposed serverless model, thereby strengthening both their mathematical reasoning and applied problem-solving skills. Another critical knowledge domain is blockchain technology, particularly the paper's innovation of a simple blockchain with hybrid validation and fault tolerance. And here students need to first recall basic blockchain concepts such as hashing, consensus mechanisms, proof of work, proof of stake, Byzantine, fault tolerance, and immutability, before comparing this heavy mechanism with lightweight validation approaches like HVFT that reduce processing costs while maintaining data integrity. And the teaching method should include demonstration of hashing function AG SHA 256 with simple data inputs so that students can see the transformation process, followed by group discussions on the trade-offs between strong security and system efficiency. To contextualize these technical insights, students should also acquire knowledge of real-world application domains such as smart cities, supply chain logistics, or disaster response, where drones must execute workflows securely, reliably, and efficiently, and where blockchain audit trails ensure accountability and transparency, with instructors encouraging students to analyze current case studies such as Amazon Prime Air, Zipline medical supply delivery, or city-level drone traffic monitoring, and to critique these cases using the aspect as framework metric of cost, deadline adherence, and security guarantees. In addition to technical knowledge, students must learn about the methodological design of the study, including how the authors model workflows as directed acyclic graphs, um, apply mathematical optimization functions to minimize cost, and conducted simulation using the iFoxSim environment with real-world dataset, as this not only deepens their understanding of modeling techniques but also introduce them to research methods that they may apply in their own projects. So, teaching can involve lab sessions where learners construct small DAGs, simulate workflows, and measure performance under different scheduling algorithms, reinforcing research-based learning. Moreover, students should be guided to critically reflect on the research findings, particularly that the aspects frame work achieved a 30% reduction in processing cost and a 29% improvement in security and privacy compared to baselines. Because understanding these results requires more than memorization, it requires learners to interpret statistical validation methods such as ANOVA test and relative percentage deviation. So educators should incorporate statistical literacy components where students practice analyzing performance data and drawing evidence-based conclusions. Equally important is fostering critical thinking about limitations and future work, where learners discuss the constraints of the current system, such as its focus on drone workflows alone and its limited modeling of dynamic bandwidth jitter, and propose their own ideas for extending the research to multi-vehicle ecosystems or probabilistic network models, thus training them to think like researchers who can build upon prior work. In terms of pedagogy, the teaching of this material should adopt a blended approach combining lectures for theoretical foundations, hands-on labs for technical experimentation, case studies for real-world context, and project-based learning for integration, while also embedding peer collaboration and reflective discussions, so that students not only absorb the knowledge but also learn to apply, evaluate, and innovate. And assessment should be multifaceted, including quizzes for basic concepts, lab reports for technical application, and group projects for integrative solutions, ensuring that learning outcomes address both cognitive and applied skills. Overall, the knowledge to be taught encompasses the principle of autonomous drone systems, the structure of edge cloud network, adaptive scheduling via reinforcement learning, blockchain-based validation mechanisms, cost modeling, simulation methods, and critical evaluation of performance outcomes. And pedagogy should emphasize active engagement, problem-based learning, and critical reflection to empower students not only to understand the SPE CES framework but also to imagine how similar blockchain AI edge integrations could transform future intelligent transport systems, making them more secure, efficient, and sustainable. Lastly, thanks for support. This research was funded by 2024 International Research Fellowship of Chiang Mai University number 67 and 616. This research work is a collaboration between the Mobile Technology Lab at the School of Economic Innovation and Technology, Christiania University College, and the Innovative Research and Computational Science Lab at the College of Arts, Media, and Technology, Chiang Mai University. This research is partially funded by Chiang Mai University. This fund is part of the 2024 International Research Fellowship of Chiang Mai University.